All right. As a reminder, we do not have a lab meeting this week. Instead, you should be finalizing your lab handout. And so remember that the submission deadline for that is this afternoon at 3 p.m. And that is the one where you are kind of taking stock of the equipment, thinking more about what it is you're trying to assess in the experiment, and then designing the experiment. I distributed the rubric that I'm going to use to evaluate that, just to kind of reinforce what ought to be included in that handout you generated. So the handout's due at 3, and then you have the rest of this week to conduct the experiment. So through Friday at 4 p.m. is when the lab will be available for you to actually do the experiment. So any questions so far about the lab part of it? Your next assignment, number 9, includes some material from Chapter 5, which we're in right now, as well as a couple of early applications of momentum, which is Chapter 6. And so we'll begin talking about momentum on Thursday's class, and so that combined assignment is due on Tuesday next week. All right, so this will be the last of our coverage in the continuity chapter, Chapter 5. Today we're just going to work through a variety of examples just to get you exposed to more ideas and more applications of the continuity relationship. And in an earlier class, we spent a fair amount of time thinking about the Oahe Dam, which is that reservoir up in North and South Dakota. And we thought about the inflow and the outflow. And in that example, we made the assumption that the cross-sectional area of the reservoir was going to be the same regardless of its depth. And this figure kind of illustrates the reality of reservoirs. And you can picture that if the water level was low, then the surface area of that reservoir would be less because I guess the way to think about it is less land area is inundated. And so, for example, if you have a very shallow depth, maybe the water is just covering from this dam and then backwards some distance. But then as the water gets deeper, the amount of area, land area that's submerged increases. So in this example, we're going to try and determine the rate that the water is rising. And the reason why I put this example in is that historically, people have had an easy time thinking about the velocity of streams in and streams out, but relatively more trouble with calculating the velocity of water rising. So what we have is the flow rate in volumetric terms, as well as the dam discharge here in volumetric terms. And then I've given you the area in hectares. Probably you're not familiar with hectares. Does anybody know what a hectare is? It's 100 meters by 100 meters. So 100 meters by 100 meters is 1 HA, hectare. All right, so what we're saying is that right now, this reservoir area is 10,360 hectares. And so if you're going to look down from above, that defines the area of the reservoir. So we know in and we know out. And remember that the basic overall formula of the continuity relationship is accumulation is the difference between in minus out. Now I'm already giving you a hint here in terms of asking for the rate of rise. And I guess you don't necessarily even need that hint because you can see that in is bigger than out. I'm not playing any games this time with like different time units or giving you one of them in mass terms. You've got volumetric flow in is greater than the volumetric flow out. So you can determine the accumulation rate. And what we want to know is what is the meters per hour that this reservoir is rising right now at this instant in time where we have a surface area of 10,360 hectares. All right, here we are. So the velocity of the rise is going to be the net difference between the in and the out. So you can think of that as the volumetric accumulation. At what rate, how many cubic meters per second, or you could even calculate it in cubic meters per hour. At what net rate is volume accumulating inside of that dam? And so the velocity of the rise, that formula Q equals VA, also applies in terms of a reservoir. If the area is the top view cross-sectional area of the reservoir, and we know that area right now is 10,360 hectares, and we can find that in terms of square meters. That's the 1.036 times 10 to the 8th square meters. So in the end, you should have a rise velocity of 0.148 meters per hour. So that would be perceptible if you, if you put a stick at the water level and came back later. You probably wouldn't be able to see it with the naked eye, but when the Ohio River levels are getting higher and higher, one thing I've done before, like when it's flood conditions, is you can just jam a stick into the bank, and then 5 or 10 minutes later you'll notice that the stick is submerged, and that's an indicator that the water level is getting deeper. So here, our 0.148 meters per hour, that's the current velocity of the rise, but that would be slowing even if the rate stays the same. The volumetric accumulation rate stays the same. The deeper that reservoir gets, its surface area will increase, inevitably. I don't think that there's a single reservoir out there where it's going to have less cross-sectional area the deeper the water gets. I mean, for that to be the case, there would have to be some sort of an overhang, but then that would be covering the exposed surface, so it wouldn't happen. So this is the current rate of velocity at this moment, but we can expect that it'll be slowing down. Any questions about how we calculated that velocity of the rise? Okay. In the lab, when we were using the orifice equation setup, we were testing the orifice equation, and we derived that from Bernoulli's equation, as you may recall, and got that the velocity of the water jet that comes out is the square root of 2gh. So that was derived by us looking at the energy at the surface of the reservoir and comparing it to the energy of the fluid jet that comes out. And of course, this velocity equals square root of 2gh. This is assuming no energy loss between the upper elevated location and the fluid jet. In reality, we have discharge coefficients that are in the neighborhood of about 0.6, 0.62. But just for that perfect inviscid fluid that obeys Bernoulli's equation exactly, here is the square root of 2gh describes the velocity as the water exits the tank. But you may recall when we were doing that experiment in the lab, we had it set up so that it was a constant head, so that the liquid level was always the same, that H wasn't varying unless we purposely raised or lowered the overflow tube. But there was always enough water going into that cylinder that that there was some water going through the overflow and the constant head through the orifice. Now, if we don't have flow coming in, then H will be decreasing as discharge exits the tank. And so what we need is an equation that will tell us how long it takes for the liquid level to fall a certain distance. And we can get that by combining the orifice equation along with the continuity principle. That is that we're going to be tracking the difference between the inflow and the outflow. Now here, there's no inflow. So basically what we'll have is that the rate of accumulation in the control volume is negative because there's only a mass flow out. So d of the mass in the control volume over time is decreasing because there's no inflow, only outflow. And now the way that we can think about this is that here, this stream out, we're calling stream 1. And we know the velocity because it's determinable by the square root of 2gh. So V1 is known based on the height of the water. And the area here at location 1 is just a function of the diameter. So let's say that we know the diameter of the opening. It's maybe the 6 millimeter hole that we saw in the lab. So this is the outflow term. And the rate of accumulation is negative because there's no inflow. And the rate of accumulation is related to how quickly the height of the column is decreasing. So dH dt is kind of like the velocity that the liquid level's going down. And then the A sub t is just the cross-sectional area of the tank. And so that's related to whatever the diameter, if this is a circular tank, for instance, if we knew the diameter of the tank, then we could calculate AT just by pi d squared divided by 4. So it's the top view area. And so this minus area of the tank dH dt, this is just basically a volumetric loss that's equal to the velocity times the area of the jet that's leaving the tank. All right, so if we substitute in our known equation for the orifice equation, so square root of 2gh, that relationship to determine the velocity into this equation, and we rearrange to solve for dt, which is what increment of time is required for the water to fall a certain height, then we can solve for that time. And you can see that it depends on the area of the tank, and so the larger the tank area, the longer it will take for the liquid level to fall some distance h. And the area of the orifice is down here in the denominator, meaning that if you have a small orifice area, then that will take longer for the liquid level to fall. But if you have a large orifice area, then that's going to reduce the amount of time it takes to fall for the liquid level to fall a certain distance. Now, let's say that at some initial time period, at t equals 0, that we have a known liquid height h. So the initial height of the water is at time 0. So that's the starting point here. And this second h is the height of the water after some flow has gone out. So this formula isn't used to calculate the distance that it has fallen, but rather the starting height and the final height of the water above the center line of the orifice. So just to put this into practice, let's consider this tank where we know it's a circular cross-section. So if we looked at it from the top, it would have a diameter of 500 millimeters. And we know the area of the orifice here. And initially, h was 2.5 meters. So here in this equation, that's the h naught, 2.5 meters. And what we're going to do is in 2 separate steps, do some calculations with this unsteady flow formula, with the orifice jet flowing outward. So in part A, we want to find out how long would it take for the liquid level to fall 1.1 meters. And so remember, this second h doesn't represent how far the liquid has fallen, but it represents the distance from the center line of the orifice up to the liquid level. So let me sketch it on the board, just because this is something that people seem to misunderstand with some regularity. So our initial case is we've got this tank. Here's our orifice, and what we have is the diameter of the orifice is known to be 15 centimeters, and the tank diameter is 500 millimeters, and it's circular. Let me kind of represent that, shown that way. All right, so we've got our 2 areas that we can calculate. And the initial height, so h naught is 2.5 meters. So that's the height from the center line of the orifice up to the liquid level. So now later, here's our tank later. We don't know how much later because we're going to calculate that. It still has the same orifice out, and it still has the same diameter. Those haven't changed, but the new height is going to be 1.1 meters lower than it was before. So H is 2.5 minus 1.1 meters. So I'll leave it to you to calculate that, but just to make it plain that this H is not the fall distance. It's the height of the water above the center line of the orifice. All right, so let me pause for a moment and calculate these two things. Here in part A, that first 1.1 meters, how long does it take for it to fall that distance? And then how long for it to fall an additional 1.1 meters? So it's going to be a different amount of time because the starting height and the finish height values will be different than it was in part A. Yep. All right. So what we're going to do is look at starting at the 2.5 down to 1.4 as the height for part A, and then part B, the additional 1.1 meters means it's going from 1.4 down to 0.3. So let's look at the fall times for that. All right, so once you find this first part, you know, the 2 times the area of the tank divided by the square root of 2g times the area of the orifice, that will stay constant. So you don't have to recalculate that for the part B. If you happen to just find out, you know, all of that, the result of that, then it's only the fall heights that need to be updated for part B. So in the first part, what we're looking at is a fall time of approximately 2 seconds. And obviously, if the orifice area was less, then that's going to increase the amount of time it takes for the liquid level to fall. Let me ask you this. What about the discharge coefficients that we know in reality the outflow velocity is affected by energy loss? And so do you recall how discharge coefficients work with the orifice equation? I think what we saw in the lab was that the Q actual equals the Q ideal multiplied by C sub D, the discharge coefficient. So the actual flow rate out is going to be less. And so what that would do is it would lengthen the amount of time it takes to fall a certain distance. And so this is what is predicted for an inviscid fluid that isn't going to experience any energy losses. But for water, our discharge coefficients are typically in the range of 0.62. And so what you could do is divide this by 0.62, and so your actual time to fall would maybe be closer to 3 seconds rather than 2, if we are accounting for the energy losses of water. All right, but I didn't mention anything about that in the example, so you should answer 2 seconds for part A. And part B, we just have different starting and finishing heights. So it's starting at 1.4 and finishing at 1.3. So I mean, in a way, this is an English problem because I'm hoping that you'll see underlined here additional 1.1 meters. So that means falling further below where it was at the end of that first increment. So if we just look at the same coefficients at the front, apply the tank area, the orifice area, G didn't change. So it's just the starting and the finishing height, and so that should be 3.19 seconds. So if I'm not mistaken, I believe you have a homework problem that's real close to this example, and there's no reason why you couldn't do it tonight and just kind of get it out of the way while everything's still fresh in your mind. All right, nozzles we've seen before, and in a previous example we looked at a nozzle that had it was intercepting the flow. So it was kind of a stagnation point where, at location 2, the manometer was causing a stagnation point where the velocity stopped and had a localized increase in pressure. In this case, though, it is a differential manometer, but it's not causing that stagnation effect. We want to find what will be the height of the liquid rise in the differential manometer. And here is the Bernoulli equation. And remember that what this manometer is measuring is the change in piezometric pressure. And just from time to time, I like to throw in, again, this idea of piezometric pressure because it's easy to forget that P sub Z, the piezometric pressure, is the pressure at a location plus its elevation multiplied by the fluid's unit weight. So just to reiterate, for example, P sub Z1 is pressure at 1 plus gamma Z1. And P sub Z2 is pressure at 2 plus gamma Z2. So therefore, delta P sub Z is pressure P sub Z1 minus P sub Z2. So here in this example, we know the velocity at 1 and the relationship between the areas at 1 versus 2. So you'll be able to find the velocity at 2 because of these first 2 bullet points. And what you need to do is, for the air with the density that's given and the manometer unit weight that's given, calculate what is going to be the deflection delta H. So this piezometric pressure equation is what determines the delta H. Okay, so you can see on the whiteboard where I've kind of rearranged the Bernoulli equation so that on the left-hand side is the change of piezometric pressure, and on the right-hand side is what we have the values for. We know the velocity at each location and the density of air, so we can find what is the change in piezometric pressure. Oh, that's not the right one. That's momentum stuff. Wonder where. All right. So just to begin, we can tell that the velocity at 2 is going to be twice as fast as the velocity of the air at 1, because we know that the cross-sectional area at 1 is double the area at 2. So if the area is double here, where it's going 30.48 meters per second, then the velocity will have to be twice as much for that volumetric flow to be conserved. And we're assuming here that there's no change in density. That's one of the assumptions of using Bernoulli's equation, is that you have an inviscid fluid that's incompressible. So we're assuming that the pressure is not affecting the change in density between 1 and 2, and it will a little. So anytime we apply Bernoulli's equation, what we observe in the real world isn't going to be perfectly described by that equation, but it's usually good enough it's worth using. So you can see that here at the top I've also calculated the unit weight of air, just because later we're going to need that when we substitute it into the Bernoulli equation. So calculating the velocity at 2 is double the velocity at 1, so 60.96 meters per second. And then here's that same algebraic kind of rearrangement that I put on the whiteboard showing how we get from Bernoulli's equation to the change in piezometric pressure on the left, and on the right, the density divided by 2 multiplied by the difference in velocity squared. So 1435 newtons per meter squared is the change in piezometric pressure. And the advantage of keeping track of piezometric pressure is it automatically reflects differences in elevation. So the fact that in this example, location 2 is elevated compared to location 1, that's already accounted for by the change in piezometric pressure. So 1435 newtons per meter squared. Now, the manometer equation is that the change in piezometric pressure is delta H multiplied by the difference in manometer density and air density. So we just, in this case, are solving for delta H where everything else is known. And you can see that the delta H is going to be 0.0914 meters. So any questions about that example? Let's talk again about cavitation. We've discussed it before. Remember that you can get water to boil a couple of different ways. One is to heat it, and when you're heating the water, what you're doing is you're increasing the vapor pressure of the liquid until it matches the vapor pressure of the, until it matches the atmospheric pressure. And then the other video that we saw one time was someone who was pumping the air out and reducing the atmospheric pressure until it matched the vapor pressure for the water, which started at room temperature water. So you can either increase the water's vapor pressure until it matches atmospheric, and then it begins to boil. And boiling is that visual phase change where you're actually seeing liquid water turning into vapor, water in the vapor phase, and so gaseous H2O. Here's a figure that shows the dependency of vapor pressure on temperature. And of course, the warmer the water is, the higher the vapor pressure of water gets, until at 100 degrees Celsius it equals the atmospheric pressure of 760 millimeters of mercury, or 101,300 pascals. Now, you can cause the water to boil at low temperatures by removing the pressure out of the headspace in, like, for example, a vacuum bell. And one place where that happens, where you have a reduction in pressure, is locations where the velocity is going really high. So consider this is similar to what we saw in the lab. You know, in the lab we had a section where water's flowing through a pipe, and then there was a contracting throat where the diameter got smaller, and because of that the velocity went up. And you saw this sag curve. I mean, you saw, because there were piezometers connected to that horizontally oriented pipe, you saw the reduction in piezometric head. So the piezometric head is how high the liquid level would rise in a piezometer to reflect the pressure in the pipe. So what this series of curves is showing is, this top one is, if you had a relatively low flow rate, and you maybe remember this, that when I was closing the valve in the lab, that there wasn't as much deflection, that we got the maximum deflection with the valve open relatively wide and a high velocity going through there. Now what this is illustrating is that if you have an extra high velocity, that the pressure inside the throat can actually decrease below atmospheric pressure. And in fact, if the velocity goes high enough, then it can go below the vapor pressure of the liquid. And when that happens, then cavitation occurs. Then that the little bubbles of vapor begin to form inside the throat. So this is kind of a risky proposition, because I've showed you pictures before of the damage to equipment that can occur when there's cavitation, like the pitting of an impeller blade, and it causes flaking of the metal, and it causes the impeller to be a little bit imbalanced and start to vibrate, and then that's the chain reaction that caused the incident at the Russian dam. So just the way to understand this is that for very high velocities, the pressure decreases and it may go below the vapor pressure of the liquid. And so here's a close-up view of what happens during that process. That the vapor bubbles form at the throat where the velocity is the highest and the pressure is the lowest. But then as the water continues to flow further to the right, because the diameter is expanding again, that means that the velocity is slowing down. And because the velocity is slowing down, you can see that the pressure is recovering, that it's going back up to what it was before. And as the pressure increases, those little vapor pockets begin to collapse. And it sends just kind of a small shock wave through the water because they collapse so quickly. It's a very sudden thing, and those shock waves go through the water and can cause damage to the pipe. Even though they're relatively small shock waves, it's enough that over a long period of time, it can cause scour and pitting and erosion of the materials. So let's do an example where we're going to calculate whether there's a risk of cavitation at this pipe throat. And so we're applying the Bernoulli equation to find out what is the pressure at 2. And then we're applying the idea of, the decision criteria is that when the pressure of the water is less than the vapor pressure, then cavitation can occur. So you'll notice that the pressure at 1 that I've defined here, 814 kilopascals absolute. And so that's not a gauge pressure. That's not measuring the pressure just relative to atmospherics as 0. This is a pressure of the liquid using the vacuum of space, meaning the absence of pressure, as 0. So the reason why we do that is for vapor pressure problems, we want to know P2 in absolute terms because the vapor pressure is given in absolute terms. So the vapor pressure of water at 60 degrees is 20,000 pascals. So if P2 is less than 20,000 pascals, then we will have cavitation at this downstream location. So I'd like you to tell me, will the system cavitate or not by finding P2? Okay, I've given you the absolute pressure at 1, and we need the absolute pressure at 2 to compare to the vapor pressure. And as long as the pressure stays above 20,000, then the system won't cavitate. But if the pressure of the water at the throat falls below the vapor pressure, then it will begin to cavitate, meaning that those little liquid bubbles, the liquid will be turning into gas bubbles. So it's essentially boiling, not because it's hot, but because the pressure of the liquid is below the vapor pressure. So what we're trying to see is if P2 is less than PV. That's the risky thing, is if it is. All right, so it's horizontally oriented, which means Z1 equals Z2. So we can simplify the Bernoulli equation. You can see here I've written Bernoulli's equation in terms of pressure head. So I've rearranged it to solve for P2. And so the terms that's causing the pressure at 2, it's going to be related to how much pressure there was at 1 plus the velocity head at 1. And then you subtract out the velocity head at 2 to find out how much pressure there will be at 2. Now, these velocities are really, really high. I set up the example that way just to have a situation where we would see the vapor pressure falling really low. The liquid pressure to fall below the vapor pressure. So there's only 1.59 meters of head available at 2. And if you multiply that by the unit weight of this warm water, since it's relatively warm water, has a different unit weight than the standard 9810 we'd ordinarily see. So 15,000 pascals is less than 20,000. So if the liquid pressure goes below the vapor pressure, then cavitation will form. Now this isn't the last time we'll talk about cavitation and liquid pressure. Next semester in 331, when we begin doing design of pipe networks, you'll again have to do some calculations looking at whether there's a risk of cavitation. And the place where cavitation is most likely is at a pump. Because if you're using a pump to suck water from a source and then increase the pressure and pump it out towards, let's say, houses downstream, then the pressure is decreasing in the direction of flow. And you'll have a low point just right before the pump. And then as the pump is spinning, the suction side of the impeller blades has a little bit even further drop in pressure. So we'll go through some calculations next semester in CE 331 where we talk about the risk of cavitation. And it'll be similar to this, where we've got a criteria that tells us how close we can get to this line before the system begins to cavitate. So here it was cavitating. And what are the implications? You can see here's an impeller that has had cavitation, and ordinarily these vanes wouldn't have the jagged breaks in them that was caused by the liquid shock waves. And this is what I was talking about before, where when there's a pump and water is being sucked in the suction side, the pressure is progressively getting lower and lower in the direction of flow. So if this line represents the spot where the pressure is 0 gauge, meaning this is 101,325 pascals, and then in the direction of flow, the pressure is going from, let's say, 100 pascals, 90 pascals, 80, 70, 60, 50. So the closer, the longer this pipe is, or the bigger the elevation difference between the water and the pump, the greater the risk is that there will be cavitation inside of the pump. Now, once the water gets onto the pressure side of the pump, then it's not going to cavitate there. It's just where the pressure is low, before the pressure has been added by the pump, that you've got the localized formation of vapor bubbles that causes this pitting and scour. Another kind of rarer instance where cavitation occurs is in the penstocks of large dams. And the penstock is just kind of a different name for the pipe that drains water from a lake through a dam. And back in the spring of 1983, there was a really, really wet spring combined with unseasonably warm weather. So it had been raining a lot and it suddenly got warm, so all the snow in the mountains started to melt in Colorado and Utah. And so suddenly there was so much water coming into Lake Powell that there was a risk of the Glen Canyon Dam having water going over the top of it. So they had to let a lot of water through the secondary spillway. And what happened was that the water is flowing at such a high velocity that the pressure decreased and these little air bubbles started to form. And just to give you an idea of how big a problem this was, these are people that are climbing down into the holes that were formed by the scour and erosion. And obviously anytime you got this level of destruction, there's a risk of kind of a catastrophic failure where this is in the proximity to the dam itself. So here's the cavitation damage, and so if this rock becomes weakened enough, then the entire hillside can collapse in and the dam could fail. So fortunately, they were able to repair this and to prevent, I think I've maybe mentioned this before, to prevent further instances where there's the damage of water that's flowing very high velocity, low pressure, cavitation occurs. They now have the ability to inject a cushion of air so that the water isn't in contact with the concrete tunnel anymore, but there's a thin cushion of air that the water is kind of floating on top of, so that as it cavitates, it's just adding a little bit more vapor into that air cushion rather than the shock wave propagating through the liquid in contact with the concrete. So it's just kind of an interesting application, and luckily this didn't cause a rupture like that dam in Russia did more recently. All right, well, that's all we have for today. Remember, there's no lab meeting, and your next homework assignment is due on Tuesday.